As you probably know by now, one of the big struggles with renewable energy is that we tend to generate a lot of it at times that we don't necessarily need it. And so energy storage systems are going to be increasingly important. Now obviously there is loads of different ways that you could store energy, but today I want to talk about a specific type, which is called thermochemical energy storage. So right here I've got a bucket filled with something called calcium chloride, which is a salt, much like sodium chloride, which is regular table salt. Now you can use this for all kinds of things. It could also be used in food. It has an E number. It kind of tastes like a really intense version of regular salt. I kind of wouldn't really recommend it actually. You can also use it as a road salt, but one of the most common use cases for this type of salt is as a desiccant. So it absorbs moisture really well. So you can use it to dry all kinds of things. And in fact, it likes to absorb water so much that if you take a bunch of this stuff and dissolve it in water, that releases a significant amount of energy, a significant amount of heat. So you throw some of that in a little cup of water, you can actually feel that it gets very, very warm. And that's interesting because that means you could theoretically use it as some kind of energy storage system. When you mix it with water, then it releases its energy, it releases its heat, and then if you heat that mixture up again with an external heat source, you could technically boil off that water again and, restore the original calcium chloride and do the whole thing over again. So you could recharge the energy storage system. And this kind of idea, that's what thermochemical energy storage is. So generally speaking, the concept of thermochemical energy storage is that you have some sort of chemical reaction or process that can go both ways, and one way it releases heat and the other way you have to put heat into it to restore it to its original configuration, and so you could use that to store a lot of energy. And this is interesting because that type of energy storage does not lose heat to its environment. You might have heard of these other systems where like just a whole load of water is being heated up to a higher temperature, or maybe a load of sand or concrete or some other medium is heated up and then you just store that heat directly. But obviously the problem with that is that as time goes on, your heat slowly leaks away to the environment, no matter how well insulated your container is. You don't have that problem if you have a bunch of this salt, because you don't store the heat directly, you're storing it as chemical energy. Now in today's video, I'm going to focus on this calcium chloride as an example, simply because I already happen to have this bucket laying around. So please realize there's plenty of other materials that you could use for this, many of which may be a far better choice for all kinds of reasons than calcium chloride, but I'm going to use this stuff because I already happen to have it, and that's a very economical way of making videos, using the stuff that you already own. Now I think one of the best ways to learn about something is obviously to experience it and to see it in action. So I've built a little small-scale test setup in the shed that I can use to actually show you this method of storing energy in real life, or at least in a video. So now without further ado, let's go over to the shed so you can actually see this working. Obviously I've already recorded this previously. Now the most straightforward way of doing thermochemical energy storage makes use of moisture that already exists in the air around us. So basically what you do is you use a simple fan to blow some ambient air through a bunch of salt, in this case calcium chloride, and in this process the salt will absorb moisture from the air, which will release the heat. Now during this, the salt doesn't get dissolved completely into a liquid solution, but rather it remains in its solid form as it absorbs the water molecules into its structure, or at least that is the goal. Then to reverse this process, all you have to do is heat up the salt again, which will drive off the water. So now let's see if we can have a go at this ourselves. So first of all, what I'm going to do is I'm going to grab a piece of black cloth that I have here, and I'm going to put this on my scale. and then we're going to weigh this calcium chloride. So as you can see, it weighs 45 grams. So the next thing we're going to do involves this weird looking contraption over here. So you can see this is an old computer fan strapped to a piece of aluminium duct. And basically this is going to force an airflow through our salt. So I'm just going to put this on the workbench for a bit. Okay, then we're going to put this over the top of it. And then I'm going to tie this to the bottom of the duct using a rubber band. Okay, so that looks all right. I'm just spreading it out a little bit so we can just put it on top of this. And so now what you can see is that when we turn on this fan, it'll blow air right through the salt and out the bottom right here, where we should get warm air coming out of this. I noticed that I just forgot to write down that it weighed 45 grams. There, that's our starting mass right there. So then, the next thing we need to do is measure the ambient temperature. So I just have a little thermometer over here, which is a very scientific baby bath thermometer, which says, I'd say that's 15.5 degrees Celsius, right? 15.5 C. There we go, that's our ambient temperature. So now what we're going to do is we're going to put the thermometer underneath the exhaust here and see what the temperature is of the air that comes out. But before we do that, we need to determine the volume flow of the air. So I'm going to tie this 25 litre bag to the exhaust of the system, just like this. And so now we simply time how long it takes to inflate the bag, and that'll tell us the airflow in litres per second or litre per minute, whatever you want. Okay, so there we go. 3, 2, 1. I think that's about 10 seconds for the whole bag. I don't know how well you could actually see the bag on camera, but I think it took about 10 seconds to fill up the bag, which I'll verify on the video later on, of course. So if I'm wrong, that will be on screen right now. Okay, so it takes 10 seconds to do 25 litres. So that is 2.5 litres per second. So now what we're going to do is we are going to turn this on. I'm going to take the thermometer and put it underneath here. Now of course it'll take a while for this thermometer to get up to temperature and display the correct value, so we're just going to let this run for a while and come back to it in a couple of minutes. Okay, so it's been just under 10 minutes, so we're just going to check the temperature, and it is at it's about 23 degrees Celsius. So we're just going to put this back, and we're going to write down that T exhaust is equal to 23 C. Now, of course, the question is, for how long are we going to let this run? And there are sort of two things to consider here. So first of all, of course, if you don't let it run for long enough, then you don't get nearly as much energy out of it. And of course, we want to get as much energy out of this as possible. On the other hand, if you let it run for too long, then something can happen called overhydration, where essentially you've added too much moisture and you sort of end up with a lumpy, sticky mess with a lot of liquid solution in there, which you sort of want to avoid. So from experience doing this a couple times before, I know that this should be able to run for about 20 minutes, which at this point means we have another roughly 10 minutes to go before I turn this off again. Alright, so it's been about 25 minutes, which is longer than I planned to run this, but it seems to be going okay, so I decided that I would stretch it for a bit longer and see if we can get a bit more energy out of this. What I have noticed though is that the temperature has gone down a little bit, so it's now just over 21 degrees, which I've also written down here so that we can take that into account later on. Now I think the reason for this is because there are some lumps of salt, some bigger lumps starting to form in there, which of course reduces the effective surface area compared to the smaller grains that we started with, and that in theory would reduce the power output of the system. So I've been trying to just pick it up a bit and shake it around to see if I could break up some of those lumps, but that's not hugely successful. It has been 28 minutes now, and I think I'm going to turn it off. So we're just going to stop it. There we go. So first of all, the temperature has remained stable at about 21 degrees, so we don't really have to do anything with that. Now, once more, I'm going to put this on the scale and weigh it. And it weighs 55 grams. So we're just going to write down that the weight, or the mass, I should say, of course, ended up at 55 grams. So now the next step is to recharge this, okay, so to dry it out again. And for this, I've made something else. It's basically a metal can with some power resistors strapped to the bottom of it, acting as a heating element, and a bit of towel wrapped around it for thermal insulation. And basically we're just going to throw the salt into this machine here, plug it into the power supply, and then heat it up until all the water is gone, or at least as much of it as possible is gone. So I'm just going to try and pick this up carefully and then just dump all of this into the container. Now, before I'm going to plug this in and start drying the salt, I'm actually going to put it on the scale and weigh it, so that way we'll be able to determine when we need to stop. Okay, so it says 620 or 621? 620, okay? So we say plus container 620 grams. So we know that we need to, let's see, we went from 45 to 55 grams. So what we want to see is for this weight to go down to 610 grams. That's how we know that the drying process is complete. So now I'm going to plug this into the power supply over here. Now before I turn it on, I'm going to write down the number that is on my little energy meter over here, which you cannot see on camera. But right now the last three digits of that meter are 676 watt hours. So right now I'm just going to turn on the power supply. There we go. Give it some power. And now begins the waiting game. Just going to put this on top of it. Give it a bit of extra thermal insulation there. And so now we just have to wait for the salt to dry. It's been roughly 2.5 hours now, and I suspect that we might actually be done here. So I'm just going to unplug this. There you go. And we're just going to weigh it to find out if we are at our 610 gram target. It actually says 608. So apparently 608. So we've actually made the salt a little bit drier than it used to be at the very start of this. Now if we look at our energy monitoring device over here, that is ended up at 709 watt hours, which means that we used, let's see, 24 plus 9 equals 33 watt hours of energy was used to do this recharging process. So now let's head back inside so that we can actually run some more numbers. Right, so now let's take a closer look at the numbers that we just collected, starting with the hydration process. So during this first test, we measured the airflow through the salt to be 2.5 liters per second with that plastic bag. Now that means that since the test ran for 28 minutes, which is 1680 seconds, the total volume of air that we moved through the salt is equal to 4,200 liters, which is of course 4.2 cubic meters, which is also 5 kilograms of air. So now I want to know how much energy we got out of it. And for that we can use this equation right here, which says that energy is equal to the heat capacity multiplied by the mass, and then multiplied by the difference or the increase in temperature. So in this case, the heat capacity of air is about 700. The mass of air that we warmed up was 5 kilograms, and then there is the difference in temperature. Now this is a little bit more tricky because remember, during the beginning of the test, during the first part, I measured the temperature to be 23 degrees Celsius, which was 7.5 degrees higher than the ambient temperature of 15.5 degrees. So during that part of the test, the delta T would have been 7.5. But then later on, during basically the last 2/3 of this test, the temperature went down to about 21 degrees, which would mean the delta T would be only 5.5 degrees. So you do need to take this into account when doing this calculation. So I kind of split it up into two parts. So first of all, I calculated how much energy was released during that first third of the test, and then I calculated how much energy was released during the last 2/3 of the test, and then I added those amounts up, and then the total amount of energy that was released comes down to 21,588 joules, which is approximately 6 watt-hours of energy. So what does this mean for the energy density? Now if you calculate that, you'll find that we had 6 watt-hours of energy in about 32 milliliters of space or volume, which means that we had 187.5 watt-hours per liter, which is also 187.5 kilowatt-hours per cubic meter, or about 675 megajoules per cubic meter. And just to give you an idea of how much that is, a fully charged electric car battery of a sort of a bigger electric car is about 80 to 100 kilowatt hours. So 1 cubic meter of space, which is like that big, that would store about as much as 2 fully charged electric cars, which is honestly not really that bad. And I will talk about how this compares to other forms of energy storage a bit later on in the video. Before we talk about that though, I want to talk about the drying process or the charging process. Now remember that I used my cheap DC power meter to measure that we used apparently 33 watt-hours of electricity to do this. The problem with this value is that it doesn't make any sense. So here's the thing. I ran that drying thing for 2.5 hours, and during the majority of this time I had set the power to about 20 watts, and actually during the first part of the process I used a bit more power to get it up to temperature a bit quicker. So how is it possible that something runs for 2.5 hours and uses a minimum of 20 watts of power and only uses 33 watt-hours of energy? That just doesn't check out. It should be more than 50 watt-hours. So then I thought to myself, there must be something wrong with that power meter. So I went back the next day to do some testing, and that is when I found this. Okay, so I'm running the setup again, this time with nothing in it. And if you look over here on our little DC power meter, you can see that it says 20 watts, 20.4. But then, if you move over here and probe the output voltage of the power controller, you can see that that is 5.07 volts. Now, for the power across a resistive load, there is an equation which is the voltage squared divided by the resistance. Now the resistance here is 3 ohms, so that means that our power is actually about 8.3 watts and not 20 watts as suggested by our meter. So I don't want to go too much into the details on why this happens, because that's not really what this video is about. I'm trying to make a video that is not about electrical engineering for once. But basically what happens here is that device that I use to control the power is a PWM controller that you can use to drive electric motors and stuff. And so it works by basically turning the power on and off very, very quickly. and the little cheapo power meter that I've been using is not sophisticated enough to deal with that properly, and so it gives incorrect readings. But now, actually it turns out 33 watt hours is probably still too much, because remember, just during that test I set it to 20 watts, and then it turns out that in reality that corresponds to about 8.3 watts, which means during that drying process the setup also would have been using about 8.3 watts, and given that it lasted 2.5 hours, that should have used about 21 watt hours then. 21 is probably too low also, because yes, it was set to 20 watts for the majority of that test, but during the first part I did use a bit more power to get it up to temperature. So given that 21 watt hours is probably on the low side and 33 watt hours is probably too much, let's cut the difference in half and call it 25 watt hours. So that means that our thermal efficiency of the system, the cycle efficiency, is about a bit under 25%. So we got 6 watt hours out of it, and it took 25 to recharge it. So where did all this energy go? Where did we lose all of this energy? Well, essentially that is simply the heat that leaked away into the environment during the drying process. So basically what it tells you is that I did a terrible job at designing my drying setup, which isn't very surprising given that it was a metal can with a bit of towel wrapped around it. So I think you could do a lot better if you actually spent some more time and effort designing a more proper setup. Okay then, so what about this? Should we start using this? Is this a useful technology? Is this going to change the world? Well, let's compare it to some other types of energy storage. So here's a little chart where you can see how it stacks up against some other things like sensible heat storage, lithium-ion batteries, and even hydrogen. And you can see that it's sort of similar in energy density to lithium-ion batteries, but of course it does it at a fraction of the cost, because this calcium chloride or other materials that you might use for thermochemical energy storage are much cheaper than lithium-ion batteries. Then there is also the advantage that it has over sensible heat storage, that it doesn't lose heat to the environment, so it can store energy for a much longer period of time. Now, of course, you might still say, well, what about hydrogen? Hydrogen looks a lot better. It's got a much better energy density than any of these things. But you have to realize that hydrogen comes with a lot of practical issues. So first of all, it's ridiculously expensive, even compared to lithium-ion batteries, especially when you factor in all the extra infrastructure that comes with it. So let's say the electrolyzers that you need to make it, or the fuel cells that you need to make efficient use of it. And then of course it is a safety risk to have 200 to 800 bars of pressurized gas that is also very flammable, which especially for residential use makes hydrogen, in my opinion, sort of a risky solution. Also, speaking of safety, thermochemical energy storage is also known for being extremely safe because it uses materials like calcium chloride and many other things that are not flammable and also not toxic, which makes them ideal for residential environments as well. But then of course there is also downsides, and one of these downsides was actually visible during my testing. So as you've been able to see, it sort of started lumping together a little bit, and when it does that, it reduces the surface area that is exposed to the airflow, and so it reduces the power output of your system. And there's other problems that can also happen, like the grains falling apart or breaking up, or even turning into a fine powder. And things like this can reduce the performance of the system, especially over many charging and discharging cycles. These issues can really become a problem. The second problem is not really a problem, I guess. It is that the energy density, although it's good compared to other types of energy storage that we have available, it's not anything that will change the world immediately. It's not an insane amount better than what already exists. And so I guess this is not really a problem. I'm just trying to sort of lower your expectations a bit, to realize that this is a good technology. I truly do believe that. I think it's a good idea to store energy this way. But it is not the magical new thing that is just going to store all of our energy in a tiny little box and it'll be amazing. That's just not a realistic thing to expect. So yeah, I think that's sort of my conclusion about this video, actually. I think that's sort of the conclusion in general that I would have about this way of storing energy. Like, it's good, it's nice, it looks promising. It does have some problems that need to be solved with, the physical properties of that salt. And then I think that we might actually see this being used quite a lot, because compared to other ways of storing energy, this does seem to have a lot of advantages. But at the same time, again, you have to be realistic. It's not some magical thing that immediately changes the world we live in. If only that existed. And that brings us to the end of this video. So if you've enjoyed watching this, then maybe consider clicking the like button or even subscribing to this channel. That'd be fantastic. And all that's left for me is, of course, to say thank you for watching.